Hello, everyone. This is the last lecture that we're going to have. This is about chapter 12, chi-square goodness of fit. Let's see if I can have this where my board could be within the frame. Okay. Yeah. So the only section out of chapter 12 that I'm going to cover for you guys is section 1, and that is chi-square goodness of fit. Chi-square is shown by this symbol, which is very similar to x, and then of course the square. Chi-square is a form of statistical test or a measure in statistical research that compares the observed value against the expected value in multi-dimensional research. So I don't have to repeat this because you guys can play back and listen to this over and over if you want. So we said that it compares observed values in any research against expected value. What is the expected value in here? Expected value, as the term expected says, whatever result that we expect to see. What is the observed? When we go to the field and we do our own statistical research, whatever that we experience, we witness, we see, those are the observed values. Example, a statistical research published by the Bureau of Statistics for the state of California publishes this research stating that, excuse me, the percentage of those households in the state of California who own one car is, let's say, 60%, and those who own two cars or more, those are, let's say, 40%. This is the example of expected values. Now, when we go to the city or the area that we live in and trying to test these expected values, we go to our own city and we do our own survey or research to see if those numbers, they do work the same in the city that we live in. The same means you're going to end up concluding that 60% of the household in the city that you live in, they do own one car, and 40% they excuse me, own two or more. When you do your own statistical research, whatever value that you come up with, those percentages for those who own one car versus those who own two or more. Those are the observed values. Okay? So what chi-square does, chi-square testing, it will test our observed values against the expected values to see if we can accept those expected values in our area. There is a formula for that. Chi-square is equal to sigma of observed values minus expected values square divided by expected values. So this is observed, and this is expected. And when we are going to do the chi-square testing, again, this is the process very similar to hypothesis. Well, this is hypothesis testing because the null hypothesis always states that the expected value is what we're supposed to accept. For example, in an example that I just gave you, H0 states that the households with one car, we have 60%. Those who own two or more, those are 40%. So this is the null hypothesis. The alternative hypothesis is if we conclude that no, that 60%, neither the 40%, they're not correct. Right? When we calculate the chi-square, then we go ahead and compare this with the chi-square of given alpha. So we compare our chi-square against chi-square of given alpha. And if they reject H0, if chi-square calc is greater than or equal to chi-square of given alpha. And there's only one tail, and that is the upper tail, only one tail and upper tail for chi-square testing. And we can either use this or we can use the p-value. Where do we get those from? Where do I get the chi-square of the alpha and the p-value? Those are in another table called chi-square table. And that is also in the appendix B of your textbook for 11th edition users. I'm going to give you guys the page number. For 11th edition users, the chi-square table is on page 979. For 12th edition users, it is on page 979. For 11th edition, it is on page 983. And I do not have the page number for 13th edition users, sorry. It is under chi-square distribution. Table 3 chi-square distribution. Now let's use an example, just an example that I used. Let's say that the state of California comes up with this with this statistic. Those who own one car, 60%, two or more, 40%. Okay, those are the expected values. Let's say that we go ahead and do, these are the expected values. We go ahead and do our own research, observed. We find out that this is 50% and this is 50%. Okay? Now, this condition that we have two types or two categories. This is called number of categories. So we have two categories in here. When we want to go ahead and find the chi-square value of the alpha or compare with our own chi-square that we have calculated, using the table, we use k minus 1. K, letter K, not C. They use it for category, but why K and not C, I don't know. So the category minus 1, that means if we have two categories, just like degrees of freedom, degrees of freedom is used in here as well. So we go to the table. So we use K minus 1 like we used to use N minus 1. And the chi-square table also is showing you those numbers of categories under degrees of freedom. This is this is the chi-square table. All right. I don't know how well you can see this. So those categories are under the column called degrees of freedom. So now we go ahead and solve for this. You see that this sigma means every single one of these are going to be subtracted from one another and squared and then added to one another. Okay? So I'm going to go ahead and do this over here. Here's the formula. So chi-square is equal to observed minus 50 minus expected. This is expected, this is observed. 60 squared divided by expected, which is 60, plus, that's because of that sigma, 50 minus 50 squared divided by 50. 50 minus 60, that's 10. Square that is 100. Divided by 60 plus 50 minus 50, that's 0. Wait a minute. Sorry guys, 50 minus 40. 50 minus 40 divided by 40. 50 minus 40 divided by 40. So 50 minus 40, that's 10. And square, that's 100 divided by 40. So this is 1.67 plus 2.5. So our chi-square calc is equal to 7, 4.17. This is the chi-square we calculate. If they tell us do the test for 95% confidence, that means alpha equal to 0.05. All right? Now we have to go to the table and find out what chi-square of the alpha is. We have two categories. We go to degrees of freedom equal to 1, and we go under the column 0.05, and across from 1, we read the value, and that is 3.841. I don't know if you guys can see that. 3.841. Under 0.05 across from 1. 3.841. 3.841. We said if the chi-square that we have calculated is greater than the chi-square of alpha, then reject. In this case, we say reject H0. What is H0? H0 states that one car household, one car owners, that goes for 60%, and two car, 40%. This is the H0. So we say that this is not accepted in the area that we live in. Sometimes when the sample is being selected, it is not based on 100 sample size, because percentage means per 100. How about when you went and got your samples, let's say that you got 200 households as your sample. If you got 200, then you have to divide your percentages either in half, because that came out of 200, or you have to multiply these by 2. All right. There's an example in the book that I'm going to use. That's problem number 3, chapter 12. Let's see. For 11th edition users, it is on page 477. For 12th edition users, it is on page 535. And for 13th edition users, it is on page 537. So go ahead and read the problem. Problem number 3. And I'm going to start solving. As you see, it says when they got the sample, let's see, it says a sample of 300 homes. So they used 300 homes, not 100. But the percentages that are given, those are per 100. So what we do is we just go ahead and multiply those percentages by 300. If we use the percentage with the decimal, if we use, like, for example, they say ABC is 29%. If we use 0.29, we multiply by 300. If we don't use 0.29, if we just use 29, we multiply by 3. Okay? So ABC, CBS, NBC, CBS, NBC, and independent channels. They did a survey, they said, these are the percentages of the viewers on a Saturday evening at 8 p.m. So this is 29% or 0.29. So multiply by 300, that will give us 87. Or you could do just 29 times 3, so it doesn't matter. And then CBS is 28% times 300. That would be 84. NBC is 25%, that's 0.25 times 300. That's 75. And then 0.18 times 300, that's 54. So we have 4 categories. Then we go ahead and do our own samples of 300. We have come up with, these are all expected values. Now observed values. ABC is 95. CBS is 70. NBC is 89. And independent channels, 46. So we go ahead and do chi-square equal to observed minus expected, 95 minus 87 square, divided by 87, 70 minus 84 square divided by 84, this is plus 89 minus 75 square divided by 75 plus 46 minus 54 square divided by 54. If you go ahead and calculate all these, your chi-square comes out to be 6.87. Okay? Now, they ask us to test with a 0.05 for alpha. So alpha is equal to 0.05. Look, we have 4 categories. 1, 2, 3, 4. We go to the chi-square table. Under 3, category number 3, under the column 0.05, the chi-square of given alpha is 7.815. So chi-square of alpha is 7.815. The chi-square that we calculated is chi-square calc is 6.87. So we do not reject the H0. We only reject the H0 if our chi-square is greater than the chi-square of given alpha. So therefore, we can say that they are kind of pretty close. 54, 46, 75, 89, 84, 70, 87, 95 in the scale of 300 samples. And if you wanted to use the p-value, this is 0.05, to find the p-value, you go to the chi-square and try to locate that 6.87. We do not have 6.87 across from degree of freedom 3 on chi-square table, across from degrees of freedom equal to 3. Your chi-square is going to be between 6.25, which is under the column 0.1, and 0.05. It's in between 0.1 column and 0.05. So your 6.87 is in between the two. The lower value is 6.251, the higher value is 7.815. So your chi-square is in between. That means your p-value is in between 0.1 and 0.05. It's in between 0.1 and 0.05. But it is closer a little bit to 0.1. And for any fraction, if it is larger than 0.05, because 6.87 is less than 7.815, which is the chi-square of alpha, that means our p-value is less than the alpha. If the p-value is less than alpha, then reject the H0. You remember for the p-value? Less than or equal to alpha, this is the rejection rule for p-value. Excuse me. Well, this is the end of all the lectures. I have been able to find out that I could do this live. As a matter of fact, I tried to do this like about 2 weeks ago, or maybe even more than that, but it took so long for YouTube. I think they do some kind of background check or something. So it took so long for YouTube to let me know that I can go ahead or approve me, let me put it this way. Every time that I requested to go live, they were asking some questions, and they sent me a code through the text message. Then I did put in the code, and I got a message that we're going to let you know in 24 hours. So it took so long. I do apologize for all the inconvenience that you have experienced throughout this rough time. I hope that all my lectures have been helpful as my lectures in class for you guys. And if you have any problem, like always, like all of you guys have been doing, emailing me, that is the quickest way to get hold of me. And I am planning to see if I can have a live broadcast on YouTube that you guys can express yourself by typing in the comments and your questions. I'm going to notify you through the news item on Beachboard and on Blackboard or Canvas for my Cal Poly Pomona students. I'm going to let you guys know through the announcements and let you know about the date and the time that I'm going to have a live broadcast. The only reason for this live broadcast is if you guys have any comment, you guys have any question. And what I'm trying to do for final exam, I'm trying to see if all of you guys for Cal State Long Beach can take it at the same time. For Cal Poly Pomona students, there's only one class that I have over there. Your final exam is going to be scheduled as it has been already scheduled. I think it's on May 14th at 3 o'clock, and you guys have 1 hour, 50 minutes. This is for my Cal Poly students. For my Cal State Long Beach students, most likely we're going to take it during the final exam week, but I would like for all my classes to take it at the same time. Again, thank you very much for being so patient and tolerating throughout this rough and tough time. I hope that all of you guys are safe and sound and well. And I hope that I would see you guys sometime in the near future. Thank you very much and have a great time. Bye-bye.